In this video, we're going to be looking at the kinetic molecular theory of gases and the postulates or the rules of the kinetic molecular theory when it comes to dealing with gases. One of the postulates that the kinetic molecular theory has is we make an assumption that the particles in a gas are so small compared to the distances between them, we can assume that the volume of the individual gas particles is zero. In the picture here you can see that with liquids, the molecules are really, really close together, and so the volume of the liquid is large compared to the distances between them, where in the gas here, the distances are so large compared to the size of the molecules, we say that essentially the volume of the molecule is zero compared to the container it is in. As it turns out, this assumption works out pretty well most of the time, but we will be discussing real gases when this assumption, where the volume is zero, is not the case. The second postulate that is in the kinetic molecular theory is that the particles are in constant motion. This is a pretty good postulate. All particles are in constant motion. In particular, the gases are going to be colliding with each other, the walls of the container, and any of those collisions exerts a force, which is pressure on the walls, and that assumption or that rule is true all the time. The third postulate is that there is an assumption that when the molecules are moving around each other, that they have zero attraction for each other. They're not attracted, they're not repelled, and so there are no forces acting on the molecules between each other. As it turns out, this assumption also can cause us some problems when we talk about real gases, but it's a pretty good assumption for most conditions or ideal gases. The fourth postulate is the average kinetic energy of the particles, or the gas molecules, is directly proportional to the Kelvin temperature. So no other property of the gas matters, i.e. the identity, the molar mass. It is only the temperature that affects how much kinetic energy the gas molecules have. Anytime we are measuring energy, it's going to be measured in joules. You'll see here the formula is 3/2 R times T, where R is the ideal gas constant and T is temperature in Kelvin. So if we want to try a practice problem here, if I was going to calculate the average kinetic energy of the gases in the room that I am in, the temperature of my room is about 22 degrees Celsius. I have to be in Kelvin to do this problem, and so the Kelvin temperature is 295. If I want to find the kinetic energy, the only variable that affects the kinetic energy of this substance, or of these gas molecules, is the temperature. So my formula is 3/2 RT. 3/2 R is 8.3145 joules per Kelvin times mole. The reason I chose this ideal gas constant value versus like 0.0821 is because the units are going to give me what I want for kinetic energy. Since I want kinetic energy to be in joules, I want to choose the ideal gas constant that is in joules, and then the temperature is 295 Kelvin. And so when I calculate this, I will get an answer in joules. You do that at home, and that is the number of joules. 3/2 times R times 295 Kelvin. Okay? All molecules, no matter what their size, are going to have a certain amount of kinetic energy based on their temperature. It does not matter their size. The actual velocity that the molecules are going does depend on their size. That is the root mean square velocity, or the speed of each individual gas molecule. This does depend on the identity of the gas molecules, and therefore the molar mass. It also depends on the amount of energy the molecules have, and therefore the temperature. So this little symbol here, this U, RMS, is root mean square and then velocity. You'll see in the formula here that we still have the constant and we still have temperature, but now we also must take molar mass into account. Again, we want to have the correct units, and so because it depends on temperature and energy, we need to have the ideal gas constant has joules in it. Temperature must be in Kelvin so that it matches, has consistent units with the R value. And then the mass of 1 mole of gas has to be in kilograms. So the molar mass has to be in kilograms per mole, again, to match the units that are in joules. It's very important to have consistent units. When you simplify all these units out, you will get units in meters per second for the root mean square velocity. So if you turn your books to page chapter 5, at the end of chapter 5, we're going to do problem number 102. And in this problem, let's go back. In this problem it says, I have 1 liter gaseous samples of H2, hydrogen, Xe, xenon, Cl2, chlorine, and O2, oxygen, and they're all at standard temperature and pressure. It says first, rank the gases in order of increasing average kinetic energy. If we go back to what kinetic energy is dependent on, we'll say kinetic energy is equal to 3/2 RT. No matter if we are looking at hydrogen, xenon, chlorine, or oxygen, if they're all at STP, they all have the same temperature, they all have the same ideal gas constant, they are all going to have the same amount of kinetic energy. You could actually calculate it and put in 273 Kelvin, but they all are going to have the same amount of kinetic energy because kinetic energy is only dependent on the temperature. Question B says, rank the gases in order of increasing average velocity. Well, that is root mean square velocity. And so we have our formula for root mean square velocity, which is 3RT over molar mass in kilograms. Again, the R for all of them is going to be the same. The temperature for all of them is going to be the same. It's molar mass that is going to be different. So in the case of hydrogen, it's 2.02 grams per mole. But again, to match units, we want to make sure we're in kilograms. So I'm going to move this decimal over 3 to the left, and I'm going to have 0.00202 grams per mole. For xenon, we'll find out that the molar mass is 131.3. For chlorine, the molar mass is 70.90. And for oxygen, the molar mass is 32.00. So I could rank these in order right now of smallest molecule up to biggest molecule. Without even having to do the calculation, I can determine that if I'm dividing by a small molar mass, that's going to give me a large velocity. This makes perfect sense that smaller molecules are going to be able to go much faster with the same amount of kinetic energy than a big molecule with the same kinetic energy. Kind of the idea that sumo wrestlers are not going to be sprinters. So the temperature at 273 is the same for all of them. Same kinetic energy, but different velocity. Question number C is, how can 1 liter samples of oxygen and hydrogen have the same average velocity? So we already know that hydrogen is much, much smaller molar mass than oxygen. If they're at the same temperature, hydrogen is going to be going much, much faster than oxygen. So what do I have to do to the oxygen to make it be able to go as fast as the hydrogen? The answer is change the temperature. Increasing temperature will give you a faster oxygen molecule. A lower temperature for the hydrogen will slow it down, and you can get the two to go the same speed. That is the end of kinetic molecular theory of gases.